In this class we will study the primal and the dual in little more detail. We will first try and write the dual for a given primal without going through the process of finding the upper estimate, and then we will define a way by which it can be written for any given linear programming problem. So, let us start with the same primal. The given problem is called primal. Maximize 10x1 plus 9x2 subject to 3x1 plus 3x2 less than equal to 21, 4x1 plus 3x2 less than equal to 24, x1 x2 greater than or equal to 0. In the last class we wrote the dual of this problem, and the dual of this problem is minimize 21y1 plus 24y2 subject to 3y1 plus 4y2 greater than or equal to 10, 3y1 plus 3y2 greater than or equal to 9, y1 y2 greater than or equal to 0. Now usually the variables x are used in the primal and the variables y are used in the dual. It is not a rigid condition or anything, just to understand that there are two different problems. Consistently we use x for the primal and y for the dual. One should also understand that it is not necessary that the primal is always a maximization problem. The given problem is called the primal. If the given problem is a minimization problem, then the primal is a minimization problem. We will also see what happens to the dual of a minimization problem. Now we make this table and we try to explain this table in the context of the problem that we have already looked at. So if we look at this example, the primal is a maximization problem, primal is a maximization problem, so primal is a maximization problem. Now we observe that the dual is a minimization problem, so the dual is minimization. So when the primal is a maximization problem, the dual is a minimization problem. Now the primal has two variables x1 and x2, the dual has two constraints here. It so happened that this primal has two variables and two constraints, so dual will have two variables and two constraints, but there is a relationship between a primal variable and a dual constraint, because when we wrote this we said we multiply the first one by a and the second one by b such that 3a plus 4b is greater than or equal to 10, and those a and b finally became y1 and y2, and because we had two constraints here we introduced two variables y1 and y2 for the dual. Therefore the number of constraints in the primal will decide the number of variables in the dual. And having defined this y1 and y2, we went ahead and said 3y1 plus 4y2 is greater than or equal to 10, 3y1 plus 3y2 is greater than or equal to 9. Therefore the number of constraints in the dual will be equal to number of variables in the primal. It is very important to understand that. In this example we may not be able to bring it out very well because both are 2 in number, but the next example that we will see, we will have an unequal number of variables and constraints and we will be able to bring this aspect much better. So we need to understand that the primal has two variables x1 and x2, the dual has two constraints. The primal has two constraints and the dual will have two variables, because for every constraint we introduce a variable. Because of these two constraints we said let us have a and b, which later became y1 and y2. Now we also observe that the right hand side values of the primal have become the objective function values of the dual. So 21 and 24, 21 and 24. So right hand side value of the primal becomes the objective function value of the dual. The objective function values of the primal 10 and 9 will become the right hand side values of the dual. So objective function value of the primal becomes the right hand side value of the dual. Now the coefficient matrix 3x1, 3x2, 4x1, 3x2 if this is represented in the form of a matrix, this will become 3, 3, 4, 3, and we realize that for the dual it has become the transpose. So 3, 4 was the first column, it will become the first row 3, 4. 3, 3 is the second column, that will become the second row. So the rows becomes the columns and columns becomes the rows. Therefore, if this matrix is called A, then here in the dual it will become A transpose. You would have learnt in algebra or matrices as to what is meant by the transpose of a matrix. So given a matrix, the transpose is another matrix such that it has the columns is equal to the number of rows, the rows equal to columns, and the rows automatically become the columns. So 3, 3 which is the first row will become 3, 3 which is the first column, and 4, 3 which is the second row will become 4, 3 which is the second column. So this is the first step in primal dual relationship. So now without seeing this, I can write the dual. I can say that if the primal is maximize 10x1 plus 9x2 subject to this, I will now go back and say that now I will go back and say that if I have this primal, now if I want to write the dual, the primal has two constraints. So dual will have two variables y1 and y2. So when I have y1 and y2, I will say 3y1 plus 4y2 greater than or equal to 10, 3y1 plus 3y2 greater than or equal to 9. The objective function will be to, because this is maximization, objective function will be minimization. So objective will be to minimize 21y1 plus 24y2, and y1 y2 greater than or equal to 0 is what you get here. So from this relationship we understand if the primal has all this, then the dual will have all this. I am also going to make a generalization that if for some reason this is the given problem, if for some reason this problem is the given problem and this problem becomes the primal, if this problem becomes the primal which I call as P, then let me try and write the dual in the same way. Now this primal has two constraints, therefore its dual will have two variables. Now let those variables be called x1 and x2. Now 3x1 plus 3x2 is less than or equal to 21, 4x1 plus 3x2 is less than or equal to 24, maximize 10x1 plus 9x2, x1 x2 greater than or equal to 0. So you observe that if this problem becomes the primal, then this problem will become the dual. So we go back and generalize that if this is the primal is a minimization, dual is a maximization. Primal number of constraints in the primal equal to number of variables in the dual, and the same table is applicable. Now if we go back and if we realize what we have done, up to all this is fine, or up to all this is we can write easily. The only place when we actually write a dual from the primal, the only place where we have to be careful and do it well is the sign of these inequalities that we have, as well as the definition of the variables. The numbers are intact. This table tells us that the numbers are intact. If the primal has 10 and 9 here, the dual will have 10 and 9 in the right hand side. If the primal has 21 and 24 here, dual will have 21 and 24 in the objective function. If the primal has 3, 3, 4, 3, dual will have 3, 4, 3, 3. But what happens to the sign, Sig and sign of these inequalities, and if there are equations, what do I do? So we should be able to write the dual of a general linear programming problem. So we explain that through another illustration. Here we consider a minimization problem as the primal. So, this problem is a minimization problem, which is the primal, and this problem has 3 variables and 4 constraints. Now, we have an unequal number of variables and constraints. We have already seen that a linear programming problem can be either a maximization problem or a minimization problem. So, this is a minimization problem. We have already seen in our earlier formulations that the constraints can be equations, it can be greater than or equal to, it can be less than or equal to. But so far in all our formulations, we have seen only variables that are greater than or equal to. We have not seen the other 2 types of variables. So, in some situations, at least while formulating, we give provision for some variables to be less than or equal to. So, in this formulation, we have now assumed x3 to be a less than or equal to variable. Now, we have also said that x2 is unrestricted. So, a variable is unrestricted if it could take a positive value or a 0 value or a negative value. For the sake of illustration, if x2 represents a profit or a net profit from buying and selling something, then the net profit could be positive or 0 or negative. So, a nice way of representing an unrestricted variable is the difference between 2 variables. Just as I explained, the net profit is a difference between a selling and a buying. So, an unrestricted variable is replaced by the difference of 2 variables. So, with this in mind, let us now write this primal further. We also observe that in the earlier instance, we were able to write the dual for a primal which has a maximization objective, all constraints less than or equal to type, and all variables greater than or equal to type. Now, here we have a minimization, and we know that we can convert this to maximization by multiplying with a -1, which we will do. But then we have mixed set of constraints and mixed set of variables. So, we now have to bring all the variables to greater than or equal to and all the constraints to less than or equal to. So, we first consider the variables. Now, x1 greater than or equal to 0 is fine. The unrestricted variable is now replaced or substituted with difference of 2 variables, which we call x4 and x5. So, x2 becomes x4 minus x5, and x3, which is a less than equal to variable, is now replaced by minus x6, so that x6 is greater than or equal to 0. Now, we see what is the effect of this change. So, the effect of change is here. Now, all the variables have now become greater than or equal to 0, because x2 has become x4 minus x5 and x3 has become minus x6, so that x6 is greater than or equal to 0. And because x3 is replaced with a minus x6, now you see that the plus 4x3 has become minus 4x6, plus 8x3 has become minus 8x6, and so on. So, all these coefficients have become negative, and this also has become negative. x2 is an unrestricted variable replaced by x4 minus x5. So, 5x2 will become 5x4 minus 5x5. 2x2 will become 2x4 minus 2x5. 5x2 becomes 5x4 minus 5x5, and so on. So, the change is captured here. The problem continues to be a minimization problem, but since the unrestricted variable is substituted as a difference of 2 variables, we now have 4 variables, which are x1, x4, x5 and x6, but all 4 of them are greater than or equal to 0, and therefore, we have now brought it to a form where all variables are greater than or equal to 0. The next thing we have to do is to bring it to a form where all the constraints are less than or equal to. Now, this constraint is already less than or equal to, therefore, we are okay with this constraint. Now, this constraint is a greater than or equal to constraint, and an easy way to make it less than or equal to is to multiply the left hand side and the right hand side by -1. Similarly, we can do this, multiply with -1 the left hand side and right hand side, this will become a less than or equal to constraint. Now, the equation poses a tricky situation. So, now the equation will be written as two constraints. For example, 4x1 plus 2x4 minus 2x5 minus 8x6 equal to 12 can be written as 4x1 plus 2x4 minus 2x5 minus 8x6 greater than or equal to 12 and 4x1 plus 2x4 minus 2x5 minus 8x6 less than or equal to 12. So, this will be written as two constraints, one with greater than or equal to 12, the other with less than or equal to 12. Now, the less than equal to 12 constraint we will keep it as it is. The greater than equal to 12 constraint we will again multiply with the minus 1 so that it becomes less than or equal to. Now, let us see the effect of all these changes. So, we now have this. Now, what have we done? The third constraint was 8x1 plus 5x4 minus 5x5 minus 4x6 equal to 10 is retained here. So, it is kept here, there is no problem with this constraint. Now, this is a greater than or equal to constraint, therefore, multiply with minus 1. So, we get a less than or equal to, the plus 9 becomes minus 9 and you will see that all these coefficients have become correspondingly negative and positive respectively. Now, this is a greater than or equal to, we did the same thing, minus 3x1 minus 7x4. So, multiply with the minus 1 becomes a less than or equal to, right hand side becomes minus 7, this minus 9 becomes plus 9 because we are multiplying with minus 1 and so on. The equation is written as two constraints, 4x1 plus 2x2 minus 2x5 minus 8x6 less than or equal to 12, which is here, and the same thing greater than or equal to 12. Now, that is multiplied with a minus 1 to get a less than equal to minus 12 and the coefficients are changed. So, now by doing this thing what we have ensured is that, and what we have done is we have changed the minimization to a maximization by multiplying this with minus 1. So, this is the maximization. So, now we have brought the original problem into a maximization problem. Now, this original primal is now made into a maximization problem where all variables are greater than or equal to type and all constraints are less than or equal to type. All constraints are less than or equal to type. Now, in the process we introduced one more variable because the unrestricted variable gave rise to another variable, and we introduced one more constraint because the equation here was written as two different constraints. So, the original problem had 4 constraints, now the modified problem has 5 constraints. The original problem had 3 variables, the modified problem has 4 variables, but we have now written it in a form where we can write the dual. So, this is still the primal, but this is a modified primal, we can now write the dual of this. Now, this primal has 5 constraints, so the dual will have 5 variables y1 to y5. This primal has 4 variables, the dual will have 4 constraints. Now, the dual will have all variables greater than or equal to 0 and all constraints of the greater than or equal to type. So, we can write the dual of this. So, this is the new primal after we have made sure I have written the same problem here. Now, we can write the dual of this. Now, the dual variables will be y1, y2, y3, y4, y5 for the 5 constraints we will have them. Now, since the new primal is maximization, the new dual will be minimization. Now, the objective function value of the dual will be the right hand side of the primal. So, minus 12x1 plus 12x2 minus 9x3 plus 10x4 minus 7y5. y1 to y5 are the dual variables. So, dual will be to minimize minus 12y1 plus 12y2 minus 9y3 plus 10y4 minus 7y5, which you can read from here. Now, we take it one variable at a time, minus 4y1 plus 4y2 minus 7y3 plus 8y4 minus 3y5 will be greater than or equal to minus 8, which is written here. Similarly, all of them are written here. So, this is the dual now. Now, this dual has 4 constraints and 5 variables. But if you go back to the original problem had 3 variables and 4 constraints. Therefore, this dual should have 3 constraints and 4 variables. So, we now reduce this dual into a form where it has 3 constraints and 4 variables. We need to do that. Now, let us do that. Here I have written the same problem. So, this is what we have as the dual. Now, we need to do a few things. Now, if we see these two carefully, these two constraints carefully, if we multiply this constraint with a minus 1, we will get 2y1 minus 2y2 plus 5y3 minus 5y4 plus 7y5 will be less than or equal to 5. So, this less than equal to 5 and greater than or equal to 5 will give us an equation. So, we do that. Now, that has happened here. So, we do this, that has happened here. Now, we also realize that we observe here that if we look at so this has been written. So, here y6 is less than or equal to 0. So, we look at the variable, we look at this variable y4. The first thing we do is this has a minus value on the right hand side. So, multiply this with a minus 1. Now, this has become an equation. So, this will have 5, this will have 4, multiply this with a minus 1. So, when we multiply this with a minus 1, we get this. Now, all these values have changed, multiply this with a minus 1, 8, 5 and 4 have happened. Now, go back to the previous one. Now, when we multiplied this with a minus 1, we would have got minus 8 here, and this plus 5 would also have become minus 5, and this also has minus 4. So, for the variable y4, all the coefficients are negative. So, now replace y4 with the minus y6, so that y6 becomes less than or equal to 0. Now, that is shown here. Now, all the 3 constraints have 8, 5 and 4, and now we realize that y4 has been replaced with minus y6. Therefore, y6 is less than or equal to 0, and the minus values have become plus values. Now, what happens is we have 3 constraints here and we have 5 variables, and we now realize that 4y1 minus 4y2, 2y1 minus 2y2, 8y1 minus 8y2. So, y1 minus y2 now can be replaced by another variable which is unrestricted. So, we do that next, we call it as y7. So, 4y7 plus 7y3 plus 8y6 plus 3y5, 4y1 minus 4y2 becomes 4y7, y7 becomes unrestricted. Now, this minimization is now changed into a maximization, which is the last thing that we need to do. So, we now maximize 12y7 plus 9y3 plus 10y6 plus 7y5 subject to all of these. So, we have now written the dual for the given problem. The given problem was a minimization, the dual is a maximization. Now, we observe that the original problem had 3 variables, the dual has 3 constraints. The original problem had 4 constraints, the dual has 4 variables. We will see some more aspects of this primal dual relationship in the next class.